My dear students, today we shall start another problem of tension member design. So the problem is design a bridge truss diagonal subjected to a factoroid tensile load of 300 kN. The length of the diagonal is 3 meter. The tension member is connected to a gusset plate 16 mm thick with one line of 20 mm dia bolts of grade 8.8. So first of all, we have to consider the grade of steel and some factor of safety. Factor of safety for material against yielding is 1.1, factor of safety against ultimate stress is 1.25, and factor of safety for materials of bolt, that is 1.25. You can find in table 5 IS 800/2007. For bolt grade 8.8, ultimate strength of bolt is 800 MPa. This first 8 indicates the ultimate stress of the bolt. 8 multiplied by 100, that means 800 MPa. Dia of hole is 20 plus 2, that is 22 mm. You can collect this data from table 19. The net tensile stress area of 20 mm diameter bolt is 0.78 multiplied by diameter of bolt, that is 245 mm square. To design a tension member, you can follow this method, and this part, that means calculation of number of bolt or calculation of strength of bolt, you can do at the beginning. After that, you can go for calculation of cross section of the member. So in this problem, we are going to do this. Let us assume the thread to be included in the bolt hole. That means in this formula, ASB is invalid. So shear strength of the bolt is FUB by root 3 gamma MB into ANB into NN. For one bolt, the strength is 90.52 kN. Now in the question, it is given that the bolt is placed in one line. So to calculate the bearing capacity or bearing strength of the bolt, we need some parameter, that is edge distance, end distance and pitch distance. Let us assume the end distance is 45 mm. Now we don't provide the minimum end distance. The minimum end distance is 1.5 multiplied by bolt hole, that is 33, but we are providing 45 mm, and edge distance is 50 mm, that is we are providing, and the minimum edge distance is 20 bolt hole multiplied by 1.5, which the provided edge distance and end distance is greater than our minimum end distance and edge distance. Now the pitch distance, we are providing 65 mm, which is also greater than the minimum pitch distance. Please keep in mind, when we are calculating end distance and edge distance, we are multiplied the constant with bolt hole, dia of bolt hole. But when we are calculating the pitch distance, we are multiplying the constant with dia of bolt only, not dia of hole. Now KB is the least value of those, you know that, and the KB is 0.681. Now VDPB is equal to 2.5 kb dt Fu by gamma MB. So the bearing strength is 89.34 kN. The strength of bolt will be minimum of the strength of shear and bearing, that is 89.34 kN. So one bolt can carry 89.34 kN load. So number of bolt is 300, that is factoid applied load, by strength of 1 bolt. It is 3.36. So approximately we are providing the number of bolt is 4. Now coming to the next part, that is the calculation of area. So now we have to choose the sectional area of the member. That's why first of all we need to calculate approximate cross section from two criteria. One is knit section failure or knit section rupture, and that is gross shear failure. And that is yielding of cross section. So from knit section fracture we can calculate the knit area, that is 1143.29 millimeter square, and we have to calculate the gross area. That's why we are adding 50% more with that, that is 1314.78 millimeter square. Now from cross section yielding we are calculating the cross section directly, that is 1320 millimeter square. I am not showing you the IS code of those clause or formula because previously I have done many times. So the large value of these two value 1314.78 and 1320, the large value is 1320. That means we have to consider this sectional area. And now go to handbook and choose the approximate cross sectional area, which is equal to or greater than this value but should not be less than this value. Now from handbook we need to check the area, that is this area 1336 millimeter square, it is greater than 1320 millimeter square. So we are considering 175.8. This is unequal rolled steel unequal angle. So let us try ISA 175.8, and the actual cross section of this angle is 1336 millimeter square. Now you have to calculate the actual load carrying capacity or the design strength of this section, because the cross section area of this member is not equal to the calculated value, it is more than that. That's why you need to calculate the design strength of this section. So from cross section yielding we are calculating TDG is equal to 303.63 kilonewton, and from knit section rupture we are calculating the TDN value. The TDN value is 321.79 kilonewton. In this formula you have to calculate first of all beta value, and beta value you can calculate from this formula, and this W is equal to nothing but 75, and T is the thickness, and Fy is 250, Fu is 410, Bs is equal to 117, because in our IS code you can see the Bs is equal to nothing but W1 plus W plus W1 minus T. So 75 plus 50 minus 8. And LC is equal to 3 into 65, that is 195 millimeter. So why 3 into 65? you can see from this bolt to this bolt, center to center distance from this bolt to this bolt is nothing but 3 into 65, because center to center distance from one bolt to another bolt, that is 65 millimeter. So we are calculating the LC, that is 3 into 65. Now the design strength due to block shear failure we have to calculate. So in this figure you can see the green surface is the AVG and this blue surface is the ATG and this green surface is AVN and this blue surface is ATN. So you have to calculate TB1 and TB2, and the minimum one, that is 313.15 kilonewton. It is the actual cross section, actual block shear strength. So minimum of TDG and TDN and TB is the 303.63 kilonewton. This is the design strength or load carrying capacity of the member. So load carrying capacity should not be less than the factorized applied load. So our factorized applied load is 300 kilonewton and our design strength of the member connection is greater than the applied load. That means the design is okay. Now in our question we don't have any other condition that you can calculate the or you can check the slenderness ratio. That's why we are neglecting this part. So you can avoid the check for slenderness ratio for this particular problem. So in our next video we shall start another design. Thank you.